Central Processing Unit. From Wikipedia, the free encyclopedia. http://en.wikipedia.org. A central processing unit, or CPU, or sometimes simply processor, is the component in a digital computer that interprets instructions and processes data contained in computer programs. CPUs provide the fundamental digital computer trait of programmability, and are one of the necessary components found in computers of any era, along with primary storage and input-output facilities. A CPU that is manufactured using integrated circuits is known as a microprocessor. Since the mid-1970s, single-chip microprocessors have almost totally replaced all other types of CPUs, and today the term CPU is usually applied to some type of microprocessor. The phrase central processing unit is, in general terms, a description of certain class of logic machines that can execute complex computer programs. This broad definition can easily be applied to many early computers that existed long before the term CPU ever came into widespread usage. However, the term itself and its initialism have been in use in the computer industry at least since the early 1960s. The form, design, and implementation of CPUs have changed dramatically since the earliest examples, but their fundamental operation has remained much the same. Early CPUs were custom designed as a part of a larger, usually one-of-a-kind computer. However, this costly method of designing custom CPUs for a particular application has largely given way to the development of inexpensive and standardized classes of processors that are suited for one or many purposes. This standardization trend generally began in the era of discrete transistor mainframes and mini-computers, and has rapidly accelerated with the popularization of the integrated circuit, or IC. The IC has allowed increasingly complex CPUs to be designed and manufactured in very small spaces, on the order of millimeters. Both the miniaturization and standardization of CPUs have increased the presence of these digital devices in modern life far beyond the limited application of dedicated computing machines. Modern microprocessors appear in everything from automobiles to cell phones to children's toys. Section 1. History. From the main article, History of Computing Hardware. Prior to the advent of machines that resemble today's CPUs, computers such as the ENIAC, spelled E-N-I-A-C, had to be physically rewired in order to perform different tasks. These machines are often referred to as, quote, fixed program computers, unquote, since they had to be physically reconfigured in order to run a different program. Since the term CPU is generally defined as a software or computer program execution device, the earliest devices that could rightly be called CPUs came with the advent of the stored program computer. The idea of a stored program computer was already present during ENIAC's design, but was initially omitted so the machine could be finished sooner. On June 30th, 1945, before ENIAC was even completed, mathematician John von Neumann distributed the paper entitled, quote, First Draft of a Report on the EDVAC, E-D-V-A-C, unquote. It outlined the design of a stored program computer that would eventually be completed in August 1949. EDVAC was designed to perform a certain number of instructions, or operations, of various types. These instructions could be combined to create useful programs for the EDVAC to run. Significantly, the programs written for EDVAC were stored in high-speed computer memory, rather than specified by the physical wiring of the computer. This overcame a severe limitation of ENIAC, which was the large amount of time and effort it took to reconfigure the computer to perform a new task. With von Neumann's design, the program or software that EDVAC ran could be changed simply by changing the contents of the computer's memory. It should be noted that while von Neumann is most often credited with the design of the stored program computer because of his design of EDVAC, others before him, such as Konrad Zuse, had suggested similar ideas. Additionally, the so-called Harvard architecture of the Harvard Mark I, which was completed before EDVAC, also utilized a stored program design using punched paper tape rather than electronic memory. The key difference between the von Neumann and Harvard architectures is that the latter separates the storage and treatment of CPU instructions and data, while the former uses the same memory space for both. Most modern CPUs are primarily von Neumann in design, but elements of the Harvard architecture are commonly seen as well. Being digital devices, all CPUs deal with discrete states, and therefore require some kind of switching elements to differentiate between and change these states. Prior to commercial acceptance of the transistor, electrical relays and vacuum tubes, also known as thermionic valves, were commonly used as switching elements. Although these had distinct speed advantages over earlier purely mechanical designs, they were unreliable for various reasons. For example, building direct current sequential logic circuits out of relays requires additional hardware to cope with the problem of contact bounce. While vacuum tubes do not suffer from contact bounce, they must heat up before becoming fully operational and eventually stop functioning altogether. Usually, when a tube failed, the CPU would have to be diagnosed to locate the failing component so it could be replaced. Therefore, early electronic vacuum tube-based computers were generally faster but less reliable than electromechanical or relay-based computers. Tube computers like EDVAC tended to average 8 hours between failures, whereas relay computers like the slower but earlier Harvard Mark I failed very rarely. In the end, tube-based CPUs became dominant because the significant speed advantages afforded generally outweighed the reliability problems. Most of these early synchronous CPUs ran at low clock rates compared to modern microelectronic designs. Clock signal frequencies ranging from 100 kHz to 4 MHz were very common at this time, limited largely by the speed of the switching devices they were built with. Discrete transistor and IC CPUs. The design complexity of CPUs increased as various technologies facilitated building smaller and more reliable electronic devices. The first such improvement came with the advent of the transistor. Transistorized CPUs during the 1950s and 1960s no longer had to be built out of bulky, unreliable, and fragile switching elements like vacuum tubes and electrical relays. With this improvement, more complex and reliable CPUs were built onto one or several printed circuit boards containing discrete or individual components. During this period, a method of manufacturing many transistors in a compact space gained popularity. The integrated circuit, or IC, allowed a large number of transistors to be manufactured on a single semiconductor-based die, or chip. At first, only very basic non-specialized digital circuits, such as NOR gates, were miniaturized onto ICs. CPUs based upon these building block ICs are generally referred to as, quote, small-scale integration, unquote, or SSI devices. SSI ICs, such as the ones used in the Apollo guidance computer, usually contain transistor counts numbering in multiples of 10. To build an entire CPU out of SSI ICs required thousands of individual chips, but still consumed much less space and power than earlier discrete transistor designs. As microelectronic technology advanced, an increasing number of transistors were placed on ICs, thus decreasing the quantity of individual ICs needed for a complete CPU. MSI and LSI, or medium-scale integration and large-scale integration, ICs, increased transistor counts to hundreds, then thousands. In 1964, IBM introduced its System 360 computer architecture, which was used in a series of computers that could run the same programs with different speed and performance. This was significant at the time when most electronic computers were incompatible with one another, even those made by the same manufacturer. To facilitate this improvement, IBM utilized the concept of a microprogram, often called a microcode, which still sees a widespread usage in modern CPUs. The System 360 architecture was so popular that it dominated the mainframe computer market for the next few decades, and left a legacy that is still continued by similar modern computers like the IBM Z series. In the same year, 1964, Digital Equipment Corporation, or DEC, introduced another influential computer aimed at the scientific and research markets, the PDP-8. DEC would later introduce the extremely popular PDP-11 line that originally was built with the SSI ICs, but was eventually implemented with LSI components once these became practical. In stark contrast with its SSI and MSI predecessors, the first LSI implementation of the PDP-11 contained a CPU comprised of only 4 LSI circuits. Transistor-based computers had several distinct advantages over their predecessors. Aside from facilitating increased reliability and lower power consumption, transistors also allowed CPUs to operate at much higher speeds because of the short switching time of a transistor in comparison to a tube or relay. Thanks to both the increased reliability as well as the dramatically increased speed of the switching elements, which were almost exclusively transistors at the time, CPU clock rates in the tens of megahertz were obtained during this period. Additionally, while discrete transistor and IC CPUs were in heavy usage, new high-performance designs like SIMD, or Single Instruction Multiple Data, vector processors began to appear. These early experimental designs later gave rise to the era of specialized supercomputers, like those made by Cray Incorporated. Microprocessors. The introduction of the microprocessor in the 1970s significantly affected the design and implementation of CPUs. Since the introduction of the first microprocessor, the Intel 4004, in 1970, and the first widely used microprocessor, the Intel 8080, in 1974, this class of CPUs has almost completely overtaken all other central processor unit implementation methods. Mainframe and mini-computer manufacturers of the time launched proprietary IC development programs to upgrade their older computer architectures, and eventually produced instruction set compatible microprocessors that were backward compatible with their older hardware and software. Combined with the advent and eventual vast success of the now ubiquitous personal computer, the term CPU is now applied almost exclusively to microprocessors. Previous generations of CPUs were implemented as discrete components and numerous small integrated circuits, or ICs, on one or more circuit boards. Microprocessors, on the other hand, are CPUs manufactured on a very small number of ICs, usually just one. The overall smaller CPU size, as a result of being implemented on a single die, means faster switching time because of physical factors like decreased gate parasitic capacitance. This has allowed synchronous microprocessors to have clock rates ranging from tens of megahertz to several gigahertz. Additionally, as the ability to construct exceedingly small transistors on an IC has increased, the complexity and number of transistors in a single CPU has increased dramatically. This widely observed trend is described by Moore's law, which has proven to be a fairly accurate predictor of the growth of CPU and other IC complexity to date. While the complexity, size, construction, and general form of CPUs have changed drastically over the past 60 years, it is notable that the basic design and function has not changed much at all. Almost all common CPUs today can be very accurately described as von Neumann stored program machines. As the aforementioned Moore's law continues to hold true, concerns have arisen about the limits of integrated circuit transistor technology. Extreme miniaturization of electronic gates is causing the effects of phenomena like electromigration and subthreshold leakage to become much more significant. These newer concerns are among the many factors causing researchers to investigate new methods of computing, such as the quantum computer, as well as to expand the usage of parallelism and other methods that extend the usefulness of the classical von Neumann model. Section 2. CPU operation. The fundamental operation of most CPUs, regardless of the physical form they take, is to execute a sequence of stored instructions called a program. Discussed here are devices that conform to the common von Neumann architecture. The program is represented by a series of numbers that are kept in some kind of computer memory. There are 4 steps that nearly all von Neumann CPUs use in their operation: fetch, decode, execute, and write back. The first step, fetch, involves retrieving an instruction, which is represented by a number or sequence of numbers, from program memory. The location in program memory is determined by a program counter, or PC, which stores a number that identifies the current position in the program. In other words, the program counter keeps track of the CPU's place in the current program. After an instruction is fetched, the PC is incremented by the length of the instruction word in terms of memory units. Often the instruction is to be fetched must be retrieved from relatively slow memory, causing the CPU to stall while waiting for the instruction to be returned. This issue is largely addressed in modern processors by caches and pipeline architectures. The instruction that the CPU fetches from memory is used to determine what the CPU is to do. In the decode step, the instruction is broken up into parts that have significance to other portions of the CPU. The way in which the numerical instruction value is interpreted is defined by the CPU's instruction set architecture, or ISA. Often, one group of numbers in the instruction, called the opcode, indicates which operation to perform. The remaining parts of the number usually provide information required for that instruction, such as operands for an addition operation. Such operands may be given as a constant value, called an immediate value, or as a place to locate a value, a register or a memory address, as determined by some addressing mode. In older designs, the portions of the CPU responsible for instruction decoding were unchangeable hardware devices. However, in more abstract and complicated CPUs and ISAs, a microprogram is often used to assist in translating instructions into various configuration symbols for the CPU. The microprogram is sometimes rewritable so that it can be modified to change the way the CPU decodes instructions, even after it has been manufactured. After the fetch and decode steps, the execute step is performed. During this step, various portions of the CPU are connected so they can perform the desired operation. If, for instance, an addition operation is requested, an arithmetic logic unit, or ALU, will be connected to a set of inputs and set of outputs. The inputs provide the numbers to be added, and the outputs will contain the final sum. The ALU contains the circuitry to perform simple arithmetic and logical operations on the inputs, like addition and bitwise operations. If the addition operation produces a result too large for the CPU to handle, an arithmetic overflow flag in a flag's register may also be set. The final step, write back, simply writes back the results of the execute step to some form of memory. Very often, the results are written to some internal CPU register for quick access by subsequent instructions. In other cases, results may be written to slower, but cheaper and larger, main memory. Some types of instructions manipulate the program counter rather than directly produce result data. These are generally called jumps and facilitate behavior like loops, conditional program execution, through the use of a conditional jump. and functions in programs. Many instructions will also change the state of digits in a flags register. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. For example, one type of compare instruction considers two values and sets a number in the flags register according to which one is greater. This flag could then be used by a later jump instruction to determine program flow. After the execution of the instruction and write back of the resulting data, the entire process repeats, with the next instruction cycle normally fetching the next in sequence instruction because of the incremented value of the program counter. If the completed instruction was a jump, the program counter will be modified to contain the address of the instruction that was jumped to, and program execution continues normally. In more complex CPUs than the one described here, multiple instructions can be fetched, decoded, and executed simultaneously. This section describes what is generally referred to as the classic RISC pipeline, which in fact is quite common among the simple CPUs used in many electronic devices, often called microcontrollers. Section 3. Design and Implementation. From the main article, CPU Design. Integer range. The way a CPU represents numbers, it is a design choice that affects the most basic ways in which the device functions. Some early digital computers used an electrical mode of the common decimal, or base 10, numeral system to represent numbers internally. A few other computers have used more exotic numeral systems like ternary, or base 3. Nearly all modern CPUs represent numbers in binary form, with each digit being represented by some two-valued physical quantity, such as a high or low voltage. Related to number representation is the size and precision of numbers that a CPU can represent. In the case of a binary CPU, a bit refers to one significant place in the numbers a CPU deals with. The number of bits, or numeral places, a CPU uses to represent numbers is often called word size, bit width, data path width, or integer precision, when dealing with strictly integer numbers as opposed to floating point. This number differs between architectures, and often within different parts of the very same CPU. For example, an 8-bit CPU deals with a range of numbers that can be represented by 8 binary digits, each digit having two possible values, that is, 2 to the 8th power, or 256 discrete numbers. In effect, integer size sets a hardware limit on the range of integers the software run by the CPU can utilize. Integer range can also affect the number of locations in memory the CPU can address, or locate. For example, if a binary CPU uses 32 bits to represent a memory address, and each memory address represents one octet, or 8 bits, the maximum quantity of memory that CPU can address is 2 to the 32nd power octets, or 4 gigabits. This is a very simple view of CPU, address space, and many modern designs use much more complex addressing methods like paging in order to locate more memory than their integer range would allow with a flat address space. Higher levels of integer range require more structures to deal with the additional digits, and therefore more complexity, size, power usage, and generally expense. It is not at all uncommon, therefore, to see 4 or 8-bit microcontrollers used in modern appliances, even though CPUs with much higher range, such as 16, 32, 64, and even 128-bit, are available. The simpler microcontrollers are usually cheaper, use less power, and therefore dissipate less heat, all of which can be major design considerations for electronic devices. However, in higher-end applications, the benefits afforded by the extra range, most often the additional address space, are more significant and often affect design choices. To gain some of the advantages afforded by both lower and higher bit lengths, many CPUs are designed with different bit width for different portions of the device. For example, the IBM System 370 uses a CPU that was primarily 32-bit, but it used 128-bit precision inside its floating point units to facilitate greater accuracy and range in floating point numbers. Many later CPU designs are similar mixed bit width, especially when the processor is meant for general purpose usage where a reasonable balance of integer and floating point capacity is required.